Chapter 7, we're going to look at section 4 today. The first 3 sections we did were about how to use the law of sines and the law of cosines to solve for missing parts of a triangle when you're given 3 parts of a triangle, like side angle side or angle side angle, or all 3 sides or something like that. So that's the kind of stuff that we did in the first 3 sections of the chapter. We're now going to change to a new topic. And in 7.4, we're going to look at vectors, geometrically defined vectors and the applications of vectors. So lot to learn in here, and vectors are helpful for people who are going to, for example, take physics classes. Physics classes will often use vectors to deal with forces and things like that. And we're going to see some examples of that when we look at applications of different types. Or if you've had physics somewhere in your past in a high school class or something, or even a college, then obviously this vectors will be already familiar to you. But we're going to use them in very limited applications here, and they do yet get used later in different applications of calculus and things like that as well. So there's lots of reasons you might need vectors in the future, and they help us understand some things in the present as well. So here we go, the basic terminology to get us started. So the first thing I'll point out is that a vector you will typically visualize like this picture here. So a vector can be thought of as an arrow where we've got a point on one end and no point on the other end. And it's sort of like you start on the point that doesn't have the arrow, and then you imagine going along the vector or in the direction of the arrow in the way that it's pointing, in the direction that it's pointing. So when you look at a vector, there's actually 2 components of a vector. And the 2 components are a vector are the length, and the direction. So when we're looking at this vector, you can imagine the direction it's going by the direction that the line is pointing. And again, you can think of that kind of like slope, if you remember slope of a line from algebra, that there's this idea that if you tilt the line higher up or further down, that you get a different slope. Well, in this case, it's the same for a vector, except that vectors also might have opposite directions. Like a line just keeps going infinitely in both directions, so it's only the angle sort of at which it goes. But with a vector, it's not only sort of, the direction is not only the slope, but also forward or back. In other words, right to left or left to right. So for example, I could make a vector that looks a lot like the one we have here if I just kind of go the same length. I was supposed to make a line. Let's see if I can try that again. It'll stabilize into a line. Yeah. And then I could put an arrow on it going in the opposite direction. And so then I would have, if we looked at these like lines back in an algebra class, these would have the same slope. But the fact that the arrow is on the other end of my little line segment here means that the vector is actually pointing in the opposite direction. So the direction is important, where the non-arrow end is where it starts and the arrow end is where it finishes. So it's going from the not arrow end to the arrowed end as a direction. And that may be right to left or left to right, depending on which end has the arrow on it. And then the other is how long is the line segment that represents the vector. That's the length. Or the word we're going to use more formally is the magnitude. So a magnitude of a vector is basically how long it is. And so they're labeling the point of the side of the line segment that doesn't have the arrow on it as the initial point, and they've labeled it here with an O. And then the line segment goes from that point over to the end where the arrow is, kind of showing the direction of travel. However, it does stop at that. So that's called the terminal point, which they've labeled with a P here. So the blue vector here goes from point O to point P. We can see the magnitude of that vector by seeing how long that line segment is. And then we can also imagine the direction that that line segment is pointing in when you go from O to P by considering like the slope of that line or something like that. So the vector, the way they've labeled the vector is from the starting point to the finishing point with an arrow on top of it as annotated here. So if you see a big O, big P with an arrow on that top, that means the vector that goes from O to P. Or instead of writing the arrow, they may just make the O and the P bold. Not all writing programs have little arrows that you can put in on them, but you can usually make text bold. So if they write a bold OP together, that means the vector from O to P, where O is the initial point and P is the terminal point. So they sum all this up by saying a vector is a directed line segment. So it's a line segment with direction. And because it's a line segment, it therefore has length, the distance from point O to point P, etc. So this is the thing we're now going to be studying in 7.4. We're going to introduce this more fully. We're going to talk about how to work with them, how to add and subtract them, things like that. And then we're going to talk about how they show up in real world applications and even how trig might be involved to help us solve real world applications of vectors. Then we might want to use trigonometric functions.
Okay, so so the vector in the plane, it says that the line is a directed line segment, like it's a segment directed on the line right here.
Yeah, so normally we learned about a line segment before when we were talking about how to make angles, and a line segment was just a line from one point to another. The only difference with a vector is that it's directed, like you want to say, where did you start and where did you finish when you drew that line segment? And you indicate that by putting the sort of arrow symbol on the end where the line finishes.
Okay. Okay.
Does that make sense?
Yeah. Okay. Thank you. I do.
Mm-hmm. Yeah. So that's what they mean by a directed line segment. It's a line segment where you add a direction by sticking an arrow on one end. But it's still a line segment. It's got length and it has a start point and a finish point. So visually, we'll just think about these as arrows. All right, so getting a little more comfortable with this. So magnitude, as we were just saying, is the length of a vector. And then they're going to show that we express that by taking the notation for the vector and putting those little absolute value symbols around it. So when we put those absolute value bars to the right and to the left of the vector notation, then that means the length of that vector. Just how long was it? That's all that means. So having described these things, now they're going to tell us when we can see that two vectors are equal. So they're equal if and only if they have the same size, the same magnitude, the same length, and the same direction. So they have to be going in the exact same direction and travel the same distance on the line segment, basically. So vectors OP and PO have the same magnitude, because if you're going between 2 points, the distance between the 2 points will be the magnitude of the vector, no matter which one was first and which one was second. But they won't have the same direction, because one of them you went from O to P and the other one you went from P to O. So even though those two lines have the same slope, as I was discussing earlier, whether you're traveling on that line segment from left to right or from right to left will change your direction. So in this case, these two opposite sort of line segment directional vectors from OP and PO, they'll have the same length, but opposite directions. So what they're showing down here is that the length or the magnitude of OP will be equal to the magnitude of PO, the vector that goes from point P and finishes at point O. All right, so basic terminology, if we have some vectors shown and labeled with like bold letters, like A and B, then we might say A is equal to B, and that should indicate, as shown in this picture here, that they're in the same direction with the same length. We see C and D, the same type of notation. They're just showing that it could be a different direction and a different length, but you still could claim that those were the same. And then, of course, if the length or the direction is different, then that would mean that the vectors are not equal. So they're introducing a new one, E here, and they show that A is not equal to E. So here was A over here. I'll point at it with a vector. And then here is E, and clearly they're going in a different direction. They may be the same length. It looks like E is almost the same length as A. I don't have a way to justify that without measuring it. But clearly, they're still not the same vector because E is going in a totally different direction as A. Then similarly, they're saying A is not equal to F. So I think the idea with E is E and A are the same length but a different direction, so therefore they're not equal. And F is in the same direction as A, but it's not the same length, so for that reason, they're not equal as well. So they're showing you that vectors are not equal if the direction is different or if the length is different. Either one of those being different will mean that the vectors are not the same vector, are not equal vectors. All right, so we're now going to think about these little arrows floating around in a plane. And the first thing we want to know how to do with them is add them. So the sum of two vectors is a vector. When you add two vectors, you get another vector. Like if you add two numbers, you get a number. If you add two positive numbers, you get a positive number. If you add two negative numbers, you get a negative number. If you add two vectors, you get a vector. The vector sum, A plus B, is called the resultant. I don't know if I've really used that word much in my life, so it's not a very common word we're going to have to use a lot or anything. But what does it look like to get A plus B? So they're showing you two ways to represent how you would figure out what the sum of two vectors is. So if you're adding vectors A and B, let's look at this example on the left. It's probably the simplest way to think about it. The way we add two vectors A to B is you imagine starting at the initial point of vector A, finishing at the end of vector A, and then at the end of vector A, you make that the initial point of vector B. And then you extend up along vector B until you get to the finishing point. And then that finishing point at the end of vector B, which was attached onto the end of vector A, is the finishing point of A plus B. So the A plus B and A start in the same place, but A plus B finishes where B would finish if you stuck the B vector's initial point at the end of vector A. So A plus B, you can imagine traveling down these vectors. To have A plus B, you would start at the beginning of A, travel down A. Then when you finished A, you'd start at the beginning of B, travel down B. And when you finished at B, after having gone on A and B, that's where the vector A plus B finishes from that same starting point. So this is the way that's shown on the left. Now, another way to visualize this is to have the vectors A and B both have the same starting point, as would A plus B. Draw them both in whatever direction they go, however far they go, and then envision how that could make two sides of a parallelogram. And so if I have vector A on the bottom, then I would imagine the same vector A on the top. And if I have vector B on the side there, then on the other side, I would imagine the same vector B. And where those meet will form the end point of A plus B, which can also be visualized when you're making these two sides as the diagonal of the parallelogram that's formed when you box out where vectors A and B go on the left and bottom. So if I have two vectors A and B and I make sides equal to their length opposite from them to make a parallelogram, then the diagonal of that parallelogram from bottom left to top right, in this case, would be A plus B. And you can see that these two different representations yield the same A plus B vector. It has the same length and same direction no matter which way we constructed it. So that's why they're showing you two ways to represent the sum of two vectors, and either way comes out with the same resultant. All right, so now they're going to play with this a little bit. The sum of a vector v and its opposite, minus v, has a magnitude 0 and is called the 0 vector. So first things to point out here, they're introducing this notation of the opposite of being just a minus in front of a vector. And so we can see that down on the bottom. If this is b here, then the opposite of b is just starting at the same point, traveling the exact same distance or having the same magnitude, but just going in the opposite direction, as we talked a little bit earlier. So the sum of a vector v and its opposite, well, if I add those two together, I get basically a point. I get what's called the 0 vector. It has magnitude 0 and it has no length. So that means it has no length because the length of the vector is the magnitude. And if it has no length, it actually has no direction either, because I can't establish a direction if I don't go from one point to another. So, but we're going to call this a vector. It's called the 0 vector, and it's basically just like a non-directional point at that point, sort of physically. Now, with that opposite defined, visualized, discussed, then we can use that to define subtraction of vectors. So as it says here, to subtract vector b from vector a, so that would be a minus b, and I'm going to put a little vector symbol on these. To have vector a minus vector b, to do subtraction, like we can do with subtraction of real numbers, we're going to think of that as adding the opposite of b. So vector a minus vector b, the way we get the result of that is by thinking about it, by taking vector a and adding the opposite of vector b to it. Those are going to give you the same thing. So they're showing here in this diagram, if you had vectors a and b, as they show here, kind of going toward the right, then the way you would subtract b from a is instead draw the opposite of b and then add those together. And then you get that nice red example diagram of a minus b, the vector a minus b. So we're going to really force ourselves to treat subtraction like adding the opposite. We've done that before in algebra with signed numbers, to sometimes making like minusing negatives and things. We change to adding the opposite, things like that. But we're going to do the same thing here in vectors. All right, so just real quick to make up an alternative example so you can kind of visualize working with this. So let's say this is vector A, and I'm going to just say that is vector B. And let's say they said A minus B, but let's say I wanted to do B minus A. Once you have these letters representing vectors, you can do A minus B, B minus A. You can add, subtract either one from the other. So this would be the equivalent of B plus the opposite of A. So then I'd want to say, well, what's the opposite of A? And that's by taking A and going in the opposite direction, the same length. So that would be minus A. And then if I take minus A and add that on to the B vector, so I'm going to try to duplicate it over here, crossing my images a little bit. Then by taking the second one and attaching it to the end of the first one, I could then draw in the sum of those by connecting those two together. So then that would be B minus A. So I drew the opposite of A, attached it to the end of the B, and I connected the beginning to the end, and that gave me B minus A. So now what's the next thing we want to do with vectors? We want to multiply them by a number to change their length. And so we're gonna, when we do that, we're not multiplying a vector times another vector, we're multiplying a number times a vector. So to distinguish that, we call that a scalar when we have a number that's multiplied by a vector. A scalar. And if I take that number, that scalar, and I multiply it by the vector, I get a scalar product. So again, this is when we have a real number k and a vector u, then k times u will be expressed as below. So when we look at k times u, let's see what's going on. The simple example tonight to start with is when you're multiplying a vector by 2. So what does it do to multiply a vector by 2? It basically doubles the length. So you're basically taking the vector you had and imagining the length multiplied by the factor of the number you're using. If you multiply by something less than 1, like a half, well, then the vector would only be half as big as it was when you started. If you multiply it by a number bigger than 1, like 2, well, then in that case, you would double the length of the vector. And the only other possibility to consider here is that if you actually allow the multiple you're using to be a negative number, you could also flip the direction. So just like putting a minus in front of A is the opposite of A, multiplying of A by a negative number will give you a resulting vector that goes in the opposite direction and also has the change of length determined by the number you multiplied by. And so if you want a vector to double its length, multiply it by 2. If you want it to be the same length but in the opposite direction, you could multiply it by -1. So what we're going to see is that -1 times a vector u is just the opposite of the vector u, because you kept the same length and you just turned it around in the opposite direction by multiplying by -1. Or as in the example they show here with the purple vector result, you could change it to the opposite direction, but also double its length. So you can add a vector to a vector, you can subtract a vector from a vector, or you can take a vector and just multiply it by a number, which will simply increase or decrease the length depending on the number you use, and possibly even reverse the direction if the number was negative. All right. So they're going to give us some properties of parallelograms real quickly here. And that sometimes helps us visualize what's going on with vectors, like they already drew one of those that I referred to earlier as a way to see how to add vectors together. So first of all, a parallelogram is a quadrilateral whose opposite sides are parallel, meaning have the same slope, basically. So if I have opposite sides and it's a quadrilateral and they're the same length and the same direction, then you get a parallelogram. So opposite sides are parallel. Opposite sides and opposite angles are equal. So when they say opposite angles, they're talking about this angle here and that angle there, compared to this angle here and this angle here. So the opposite angles will be the same. The opposite side lengths will be the same. And the sides themselves, when you consider them as lines, have the same slope. They're parallel. Then, if you consider the diagonals of a parallelogram, again, these are properties of a parallelogram, the diagonals, which are drawing across one diagonal and then the other, there's 2 of them. They bisect each other, so that means the place where they meet in the middle is at the halfway point of each, but do not necessarily bisect the angles of the parallelogram. So the way I've drawn it here, for example, you could see that this bottom right corner, that angle is shorter than that angle. So that angle did not get split in half, but the lines, when they cross, they split each other in half. They bisect each other. Now, if you have a square, then you bisect the angle as well, because then the diagonals form 45-degree angles with the sides. But in a parallelogram, they don't necessarily cut the angles in two evenly, but they do cut each other when they cross in the middle. The diagonals themselves cut each other in half with equal lengths on either side. So these are some properties to help us maybe in our discussions later when they show up in examples. And I believe that's the complete description. You see if I'm sure about this. They introduced this thing called the equilibriant, but other than that, I think after that, we're basically just doing examples. And of course, trig will become involved. So let's take a look at this first example and see where they're going to lead us. So they're already talking about forces. And so that may be something that's uncomfortable for people who haven't had any experience to physics. In fact, it usually is. A force you can think of as some sort of pressure or weight or something like that. You can create a force by pressing on something yourself. For example, if you go deep in a pool, you can feel the water pressure pushing on you. That's the force of the water pressure. The fact that we're pulled down to the ground, and if you jump up and you get pulled back down, that's the force of gravity. That's what creates sort of your weight. So you can have a physical force often created by something pushing on something else or something pulling on something else, like gravity's pulling you down to the surface of the earth. Water pressure is pressing against your body, things like that. And so I just want to point that out because they kind of jump right in here with an expectation that people are comfortable with the idea of forces and how they're measured. And that may take some getting used to, and you may feel uncomfortable with that for a while. If so, that's normal. That's okay if you haven't ever thought about this or been exposed to this before. So newtons is one of the ways to measure a force. Let's just leave it as a unit of sort of force and not worry about how it's composed for now. So it says two forces of 15 and 22 newtons act on a point in the plane. So here's our point in the plane. And the way they're illustrating the force is by the number of the force is how strong the force is against. So imagine you're pushing on something, then that's like the number is how hard you're pushing on it. But the number doesn't tell you in which direction you're pushing on it. Am I pushing on it on the right or on the left or up or down or what? So in a plane, you could be pushing left to right or up and down. And so the way we indicate the direction of the push of the force is with a vector. The vector's direction is the direction the force is applied to, in this case, to the point P, and then how hard you're pushing, we're going to use the magnitude of the vector to show you the strength of the force that's pushing in that direction. You could even imagine a person standing and looking down on their head from above, and then two people come in at an angle and push on them, then that could be represented as vectors of direction and magnitude for those pushes being applied to that person. So it does sort of say a Newton is a unit of force that equals 0.225 pounds. Again, so pounds is a force of weight. And so a Newton can be thought of as like the force of gravity of weight of pounds. And then this gives you a sense that it's like around 1/4 of a pound. So if they have 15 Newtons, that's going to be something a little less than 4 pounds of weight pushing, but in a particular direction, etc. Now, so we have these two different forces acting on the object. We know the size or the strength or the power of the force pushing on the point P. And then they also tell us the angle between the forces is 100 degrees. So that means if I were to draw the direction of these vectors, I would need to draw those directed line segments so that they both begin at point P, because that's where the pressure is being applied. And then as they leave point P in these two different directions, there's a 100-degree angle between those two different directions. So that's a lot to absorb, to think about. Hopefully it's comfortable for some of you, but if not, hang in there, try to make sense of it. And as you see more examples, hopefully it'll get even better. So the angles of the parallelogram adjacent to P measure 80 degrees. So what are they talking about? They're talking about this angle up here and this angle down here. The 80 got erased somehow. That's not me erasing, right? Yeah, I can't erase the 80. On the slide, it's erased. Interesting. Anyway, so this angle is 80 degrees and this angle is 80 degrees. So how do we know that? It says because the adjacent angles of a parallelogram are supplementary, use the law of cosines with either triangle. Okay, so how do we see that in this case? So here's one other way to think of it. What they're saying is, you may remember we did these things, transverse axes and opposite angles, way back when we first looked at angles. That's what's going on here. What they're showing is that these two angles here, like that, are going to be the same as these two angles here, because as we saw, opposite angles in a parallelogram are the same. And so this parallelogram cuts these so that this angle measurement there will be the same as that angle measurement there. And so when we look at this triangle in the upper right that's formed here, just sort of draw it quickly like that. In that triangle, then this angle plus this angle, those are two angles in a triangle that then have to add up to 180. And we know that the small angle and the big angle here add up to 100 because we were told 100 degrees is the total in this upper left corner here. So that means the smaller portion of that and the bigger portion of that have to add up to 100. And that means there's 80 left over for the remaining angle in that triangle. So let me erase all of this, scribble, 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 so the picture can be seen more clearly and see if that makes sense. So again, if this total is 100, and you get that 100 by adding, we'll say, little angle A and little angle B here, that means A and B add up to 100, but we also know that little angle A is repeated over in this corner over here. So that means angle A and angle B are 100 in this triangle, whoops, leaving 80 degrees for the remaining angle up there since they have to add up to 180. So what did they tell us and what did we conclude on this first slide? They told us that we have two forces being applied to a single point and that the angle between those two forces' directions is 100 degrees. Well, what we want to do is find, sorry, I should have led with the goal, which is in the statement, find the magnitude of a resultant, meaning if I add those two forces together, what is the size of the resulting force between the two of them? So if two things are pushing on this, then that combines together and creates an overall force. And we can see the direction of it here, but they're basically just asking for the magnitude of the combination of these two forces. What is the total? What is the magnitude of V in the picture here? Here's the V is the sum of these two vectors, and what is the magnitude of the, as they refer to it, the resultant. So the reason they're creating this triangle and filling out the missing side is that if you make this parallelogram and you make these two triangles, then the diagonal resultant is one side of a triangle where we know side, angle, side. And we learned how to fill in the missing pieces when we had side, angle, side. Specifically, you can find the side that is unknown with side, angle, side using the law of cosines. So if I have side angle side, then the law of cosines allows me to form the missing side, not using the same letters here, but you may recall a squared equals b squared plus, whoops, c squared. This was the law of cosines minus 2bc cosine of angle A. So if angle A is between sides B and C, then you can put the angle A and B and C into this expression, and then that will give you the square of the side you don't know, and you square root, and then you've solved for the side you don't know. So that's what we're going to do here, as we learned in the 7.3. That's what we'll do here to find the length of that third side of the triangle, which will in turn be the magnitude of the resulting force vector when you add the two forces applied to point P. So they'll do that on the next slide, I believe. They'll at least fill out the, oh good, they have a diagram too, that's good. So they show, okay, in this picture, V is the side we don't know, and the sides we know are 15 and 22, and the angle opposite V is 80. So plugging in the 15, the 22, and the angle into the cosine, you're applying the law of cosines, and that gives you what V squared is. And then if you take the square root of that, you can get the approximate magnitude of V, in this case, to be 24 newtons, being the units measured here. All right, so just quickly then, what did this look like if they hadn't already filled in a bunch of the pieces? So if I have 10 newtons in this direction, and I have 17 newtons in this direction, and the angle between these is, we'll say 80 degrees, then they can say, what is the magnitude of the combination of these two forces applied to this thing at point P, whether that's a person or an object or whatever. And so the way we would combine those is try to imagine what is the sum of these two vectors, which is this diagonal. So that would be the sum of those two, which they called V. And so we would want to get the magnitude of V. And so,
Professor.
yes, question.
So now, what made them say that cos, when it was A was 80? Because it's in a different triangle. So how did you know that it was, the angle A?
Great question. All right, so let me see if I can show in this example that I'm currently doing here. And then if that still gets confusing, I'll follow up. So in the picture here, we have this V that's created by adding the forces of the 17 newtons and the 10 newtons. And the 17 newtons and 10 Newton force vectors are separated by an angle of 80 in total, right? All right, so what that means is that, let's see if I can put it in this picture, that this angle here, this short little angle that I'm sketching in orange here, plus the bigger part here, those add up to 80. Does that make sense?
Yeah, that makes sense.
So those add up to 80. Well, that short vector, the big part of that is repeated over here.
Okay.
Because we have parallel lines, and this goes back to when we first introduced angles. And when you have a line that crosses parallel lines, then this sort of where transverse lines are equal in magnitude.
Okay.
In any event, so that means that this angle and this angle add up to 80.
Okay.
So the angle down here, which is opposite V, that's the one we need to have in the cosine. The one that's opposite V, that's the rest. So if the other two angles in the triangle are 80, then that one has to be 180 degrees minus the total of the other two of 80, which is 100 degrees. Because we have this triangle here. Here's our triangle in black, this side, the side that we want to figure out the length of, and this side.
Okay.
And in that triangle, the two littler angles add up to 80. That leaves 100 degrees for the one in the corner there, that's opposite side V. Does that make sense?
Yes, that makes sense. Thank you.
Okay. All right, so then we know that this side is length 10. We know this side is length 17, and we know the angle between those is 100 degrees. So we can use those to find the length of V. And we would do V squared is equal to 10 squared plus 17 squared minus 2 times 10 times 17 times cosine of 100 degrees. And like they did here, we would solve that for V, and that would give us the magnitude of the force vector created by the other two forces pushing on the object. Questions?
Just so I know I have this correct. So the forces are just going to be like the lengths of the vectors, like when we're doing the problem, right?
Yes, the way this vectors allow you to model real world force situations is by when you have the length of the vector representing how hard it's being pushed in that direction. And when you apply two vectors with that application, then when you add those two vectors, you get the same thing as if you had added those two forces, meaning when those two forces are pushing on the object, the end result on the object is that you get a power of angle V, and you get a direction of movement of angle V, of vector V. And so the idea here is that if you apply those two forces on the object, what ends up happening is P gets pushed in the V direction, and in this case with 24 newtons of pressure.
Thank you.
To make all that work out, we're visualizing the length of directors as the magnitude of the force as well as their direction. Does that make sense?
Yeah, thank you so much.
Okay, we got about 10 minutes to see where we can follow these examples. So the equilibrant, sometimes it's necessary to find a vector that will counterbalance a resultant. Well, too many vector words, which we don't really use much. Counterbalance, when you add two vectors together, you get an answer. Sometimes we want to find something that counterbalances that. Why is that? Well, because then you counterbalance those two forces. So if I have an object here and I have a force pushing this way and I have another force pushing that way, well, we could imagine that the resultant of these forces would be, something like this. So this object is getting pushed in that direction. However, I can counterbalance that so it doesn't move, so that it doesn't get moved by these forces if I go in the opposite direction with a new force of the same size. So basically they're saying I could balance out the resultant of these two forces if I have a third force that's in the opposite direction of of what you get when you add the other two. And if all three of those are acting together, then there's a perfect balance, because the red vector is a perfect balance in the opposite direction of what the two black vectors are producing together. And if that was the case, then all three of these would basically balance each other out and nothing would move. So you'd be sort of pulled in opposite directions the same amount, so you end up not going anywhere. It's like a tug of war where the balance was perfect, so the tug of war rope isn't moving in either direction. So that's what they're trying to get at here. So the equilibrant of a vector u is the vector minus u, but specifically they're going to make it where the equilibrant is of a resultant, where you had something that was the sum of two vectors, and you find out a single vector that would counterbalance or be opposite to the sum of two other vectors. That's the situation they're describing here. So let's look at their example. Here it is. So the two blue vectors are the vectors they're starting with, and the resultant of these two blue vectors is going to be what they're labeling as the V vector here. If you added the A to B let's see, there's no point down there. If you add the two blue vectors together, you get this vector to the right, the v vector of length v. And so then they're saying to counterbalance that, to get the equilibriant, we would need to go to the left by the same size, so that would produce the negative v to counterbalance the sum of the two blue vectors here. So that's the situation. And so they're describing it by saying, find the magnitude of the equilibriant of forces of 48 newtons and 60 newtons acting on a point A. So there's our point A right in the middle, and you've got 48 and 60, and there's 50 degrees between them. So it says if the angle between the forces is 50 degrees. Then find the angle between the equilibriant, the one going in the opposite direction, the one that balances everything out, and the 48 Newton force. So they're referring to find the angle, and that angle is this alpha angle that they're showing right there in the picture. So basically they're saying if you had a couple of force vectors acting on an object, what angle and force would be necessary in order to balance that out so that the object doesn't actually get pushed around anywhere? And this is a diagram to illustrate that. Well, finding the magnitude of the minus v vector, it'll be the same magnitude as the v vector, which we just found in the previous example. So we just found the size of the vector you get when you add the other two vectors together with a given angle between them. So we would do that same thing to get the magnitude of v, and that would therefore give us the magnitude of negative v. And then we just need to figure out this alpha angle, and then that's what they want in this problem. So we would, as before, use the law of cosines to find the magnitude of v, and this turned out to be 98 newtons in this case, when there's 50 degrees separating the 48 and the 60 Newton vectors. Then the resultant of adding those together is 98 newtons. That means to counteract that 98 newtons to the right, you'd need the negative v vector to have 98 newtons to the left. And so that's the same exact value we got if you were adding the vectors together. Well, then the opposite of adding the vectors together will have the same magnitude. But we want to get the direction as well. And so how do we get this direction? So the required angle, again, we're talking about this angle alpha here, which goes from the blue 48 Newton vector over to the one that cancels everything out. The required angle can be found by subtracting angle CAB. So here's C, here's A, and here's B. So this angle here is angle CAB. That's angle CAB is this thing here. Can be found by subtracting angle CAB from 180, because we know that V and negative V are opposite. So that means from V over to negative V is 180, and alpha is just missing the CAB angle. So if we can find CAB and subtract it from 180, then we can solve for angle alpha there. And then it says use the law of sines to find this angle that we need, CAB. So to find that angle, we know the opposite side is 30. So we could do that sine of angle CAB is to 30. I'm sorry, 60. I said 30 is to 60. That side there is 60. So the sine of the angle divided by the opposite side, where we know the opposite side. And then we also know 130 degrees is an angle. And we know the length now of V, which was 98. Yeah, 98. So that would be then that the sine of 130 degrees is opposite V, and V is length 98. Just set it 98. So by setting that up in the law of sines, we can solve for the sine of angle CAB and figure out both an inverse sine angle CAB subtract from 180 to find alpha. So there's a little process we go through, but they spell it out for us with a little help, hopefully from me. So here they're going through that process. So sine of angle CAB over 60 is equal to sine of 130 over 98. And then if they solve, they got approximately 28 degrees for angle CAB. That's this one here. And so then they can get alpha by subtracting that from 180 and getting 152 degrees. So by putting these two things together, if we have two forces, one of 48 newtons and one of 60 newtons applied to a point or an object, and the gap between those is 50 degrees, then we can perfectly counterbalance both of those forces by applying a force of 98 newtons at an angle that is 152 degrees counterclockwise away from the 48-degree angle of that force. And then if you put that added force to the other two, they'll all balance each other out.